But I would like to start today with Optix. So let me drop in the chat. So hopefully everybody's got a version of Python that they're running on their computer. So you want to be using Python 3. So this is on github.com/usuarrow/optix. This is access to that code. And you can pull this as a repository, like you do with GitHub, or you can also just go up here and download the zip file. And that's what I did to get the code. And then once you download it, there's instructions down here for installation. So after you've downloaded it and open the package, then you just type in, you change to that directory, type in Python setup.py install, and it will install the package, and then you'll be able to call it from anywhere. So anyway, here's information or instructions for getting the code and installing it, whether you're downloading it or cloning it from the repository. Okay, so will you guys let me know when you have that installed? All right, so we've got a couple. So we're pretty lucky to have the author of Optix with us today, Corey, and he's going to walk us through a few things with Optix. So Corey, I'm happy to, so let me show you what I have up on my screen. I have the help, help inside of Python that you have. So we can use this, or if you'd like to just share your screen, Corey, you can introduce us to some of the settings. Basically, what I'd like to do is just walk through this this help file, and explain what each of the settings are here.
Yeah, and let me go ahead and share my screen. I think that'll be a little more straightforward.
Okay.
Alrighty. Okay, can you guys see my terminal?
Yep.
Yep. Let's see.
Okay, so before we move on here, I just want to make sure, does everybody have this installed? Because I'd like to actually be running some things on it today, so you feel comfortable with it. I know Corey's got it. I saw 2 others. Okay, Ben's working on it. Okay, Ammon, how about you? Okay, can't quite find where the zip is at. So if you go to that link at the top, there's a green button that says code. And you click on that, and then at the bottom of that drop down, it says download zip.
Right here, where I'm showing you.
And then you'll just need to open that and put it somewhere on your computer. It really doesn't matter where you keep that source code. You'll just then need to go to that in from a command line sense, go to that folder and then type in the installation command, and it will install it.
And then once you've got it installed, you can access it. Installs it as a Python module, and so you can access it from anywhere on your machine.
Is it the exact same install procedure as like mockupx or RFORL database, Corey?
Yes, it is.
Okay, cool.
Yeah, I wrote Optix way back in the day when I didn't know anything about Python programming. So the installation instructions here in the README are a little different than what you see in the later packages I developed, but anyway, you can install it using either set of commands.
So I just
and we need to get prep.
Chat.
we need to give proper credit here. Optix was first written by Dr. Hunsaker and then was greatly improved upon by Josh Hodson, and then I came along and rewrote it. So I'm not the sole author here.
That's true. That's true. So I wrote my version in Fortran a long time ago,
Mhm.
and then Josh, I think he edited the Fortran version of it, if I remember right.
Yeah, I can't remember if he's kept it in Fortran or if he ported it to Python.
Uh-huh. Yeah. Anyway, but Corey is basically the sole author of the code that we're going to be using today, and there are some benefits to it over the libraries in SciPy, and so that's why I want to spend some time with it. Although there are some definite benefits of what SciPy has to offer as well, so we'll cover that. You know, you want to be using the right tool for the right problem, basically.
Yeah. Yeah.
Okay,
Well, and maybe
how
I
we
can
doing,
mention.
Hammond?
A hard time getting it to run from my shell. But I'll keep working at it. You guys can keep going.
Okay.
Do you want me to get started then?
Okay, yeah, go ahead. Thanks.
Uh-huh. So yeah, like Dr. Hunsaker said, Optix presents a few advantages over what's in SciPy.optimize. One of them being, I mean, so far as I can tell, SciPy.optimize doesn't have the Grg algorithm, which is a really useful algorithm, especially because of what we mentioned earlier, that it makes sure you're always staying inside of feasible space. So you can have some instances where you're going to have to quit your code, or your code is going to quit on you before it actually reaches the optimum. And it'd be nice to be able to use whatever you manage to get to. So if you're using something like SL or SQP or SLSQP, that intermediate result may not actually be feasible. But if you're using GRG, then if you quit midway through, you're guaranteed to have a better result and have a feasible result. So that's something nice about that. Another big part of what...
Could you repeat that wording, Corey? I just got stuck on the first portion just so I could understand the difference between the three methods, if that's okay.
Sorry, understand the difference between what?
Or like the specification on the conversions that you just said.
Oh, so if you're running a really big optimization, and say you're each evaluation of your objective function takes maybe 20-30 seconds, it's going to take you a really long time to run this, and say your machine crashes partway through, or your objective function throws some big error and everything dies, then even if you're like 26 hours into this optimization, you'd like to be able to take advantage of all that progress that's been made. And with the GRG algorithm, you're guaranteed that even at the end of that, even at this intermediate step, you're going to have a feasible, usable result that is better than what you started with. With SLSQP or SQP, it's not guaranteed to be feasible. It's not guaranteed to satisfy your constraints.
Okay, thank you.
Yeah. So yeah, that's one of the advantages of the GRG algorithm. Anyway, one of the other big things that I guess was a focus in the development of Optix, or at least this version of Optix, was the ability to do multiprocessing. So for these gradient-based algorithms, you end up doing a lot of objective function evaluations almost simultaneously. So if you've got if at each step you're having to calculate a gradient, if you're doing that using central differencing, then you need to perturb in each direction for each of your design variables. And so say you've got n design variables. For a central difference, you need to run 2n evaluations of your objective function. And so if your objective function takes 30 seconds to run, you're going to be sitting there waiting for 2n times 30 seconds just at a single step of the iteration. And it's not, those don't have to happen sequentially. Those can happen all simultaneously, and you can get a lot of savings out of that. Also, the same thing with like your line search. Once you figure out, okay, what is my optimal search direction? Throw out a whole bunch of points in that direction, and you can you can run all of those points simultaneously. And so Optix has a lot of multiprocessing built in under the hood to be able to do these computations simultaneously. And that's, again, that's not something that SciPy has. You can, in SciPy, give it a gradient function, and you can give it a Hessian function even. And what you can do is you can just use central differencing for that, but you can implement the multiprocessing yourself. That's one way to do it. But again, this is all built in Optix, and you don't have to worry about that. So anyway, once you have Optix installed, I'm just going to be in the Python interpreter for right now. We can import it. I'm going to OX. And all of the documentation, the instructions for Optix are stored in the doc strings. So these are that triple quote string that you find right after the function definition in Python. You access those by in your interpreter. You type help ox.minimize, and this brings up what the minimizer function is and what its arguments are. And I'll go through all of these, and if you've got any questions, just pipe up and ask them. Anyway, at the most basic level, so we call minimize, we give it a function. So this is our objective function to be minimized, and then we give it an initial guess. So x0, where do we want to start the optimization? You can then pass it a whole bunch of keyword arguments that specify, okay, what method do you want to use? What are the settings for that method? A whole bunch of other different things. You can give it a tuple or a sequence of what's called args, and this it will unpack and give to your objective function at each step. So if you've got an objective function where, say, the first argument is your design variables, but you've also got a couple more arguments to that objective function that's like, atmospheric parameters, such as, air density, altitude, that kind of thing, then you can still pass those through by giving it to this args tuple here. Then this is where it gets really interesting. We have method. So we can, like Dr. Hunsaker mentioned, we can use 3 methods in Optix. There's BFGS, which is again unconstrained, and then we have, for constrained problems, we have SQP and GRG. The defaults are BFGS if no constraints are given, or SQP if constraints are given. You could then pass a function called grad that returns the gradient of your objective function. So this is exactly like SciPy Optimize. You can give it your own gradient function. If you know the gradient, if you can calculate that analytically, then you can pass that in and give yourself some savings there. This function is not currently used. That one is not currently implemented. Optix, the documentation for Optix has a lot of unfulfilled potential, if we want to say it that way. But anyway, and then you can give it a list of constraints. So if you're using SQP or GRG, and what you do for that is you give it a dictionary you give it a list of dictionaries. So each dictionary defines one of your constraints, and inside that dictionary you give it 3 keys. You tell it the type, EQ for equality or NEQ for inequality, and if you specify that it's an equality constraint, then the function that you give it has to equal 0. And if you give it an inequality constraint, then you're telling it the constraint function has to be positive. So you give it this. The next thing you give it is fun. You give it the function, and that's that constraint function. And this has to be in terms of your array of design variables. And again, if you have specified an equality constraint, then it's going to make sure that this function is equal to 0. If you give it an inequality constraint, then it's just going to make sure that that constraint function is positive. We then have, you can tell it when to stop the optimization. We have a termination tolerance, which is saying if my step size, so between 2 iterations, how much I've changed X, if that falls below this termination tolerance, then quit, you're done. You can also alternatively specify a gradient tolerance. So if anywhere your gradient, the norm of your gradient vector falls below this tolerance, then it will quit there. So that gives you a little bit of power over when it can actually be, when it actually says it's done. You can specify whether or not you want it to be verbose, and that's just saying, okay, do you want a bunch of information to the command line? Central differencing is a flag for sorry, whether or not you want to use for differencing or central differencing for your finite difference approximations. Final tag. What Optix will do is at each iteration, it will output some results to a couple different files. It will track your gradient vector at each step, and it will track your iteration, or at each step, it'll track the current guess and the current objective function value, and it'll write those out to a couple of different text files. This file tag is, you can give it a tag to append onto those file names so you can keep track of things. That's just for you to be able to organize things a little better. Max processes, so this is that multi-processing thing. This is saying, okay, this is the most processes I ever want to use. So if you've got, 32 cores on your machine, but you want to be able to run some other stuff while this optimization is going, you could specify max processes, 16 or 8 or whatever you'd like. DX is the step size used for your finite difference approximations. Max iterations is the maximum number of iterations to go through for the optimization. And then num average is something I added. I don't know if it'll ever be used. But if you've got an objective function that's a little stochastic, I guess you would say, it's not returning the same result every time, then you can tell Optix to run the objective a few different times and average the result, and it'll take that as your objective function. Anyway, like I said, I don't know if this has ever been used or will ever be used, but if you need it, it's there. Any questions so far? Okay. Then once it's all finished, like scipy.optimize, it'll return an object that contains all of this information. So it'll tell you your optimal point. It'll tell you the value of the objective function at that point, tell you whether or not it exited normally, and a message about how it exited if there is anything that you need to know. And then it'll give you the number of objective calls and constraint calls. So you can kind of track, how much computational expense is going into this. So that's that's kind of all the general settings. For each one of these algorithms, though, there's a couple of different, there's arguments that are specific to each one of the algorithms. So we can go through those. For BFGS, we've got nsearch. So like we said, for BFGS, it picks a search direction, and then it throws out it does a line search in that direction. And here you can specify how many points it's going to throw out in that search direction. You can also pick the spacing for the first iteration of the first line search. So BFGS will automatically update the spacing on that line search. Depending on the results it's getting, it'll stretch those points out further or shrink them down a little bit. Anyway, so that gives you some control over how you want it to start off. You can also set this parameter set to reset alpha. So alpha is your step size. You can reset that at each iteration. So each time you find the gradient, reset this step size, and then you can adjust as you want, because it'll adjust that line search step size added or within each iteration as well. Because what it's trying to do is, once it's found an optimal direction, it's going to execute a line search. And then if it doesn't find a minimum within that line search, it's going to stretch it out or shrink it down in order to bracket a minimum. And then once it's able to bracket a minimum, then it'll actually find, or then it'll quit the line search and move on to the next iteration. Alpha molt is just, so at each iteration of the line search, it's adjusting that step size to try and actually bracket a minimum. Alpha molt gives you control over how much you're changing that step size at each iteration to be able to bracket that minimum. This is a parameter for specifying the line search type. So you can do either a bracket or a quadratic. So bracket is where it just it throws out those points, does line search, executes the objective function, and then if it's bracketing a minimum, it'll take the bottom 3 points, so the 3 points that bracket that minima, and find the vertex of the parabola defined by those 3 minimum points. If you pick quadratic, on the other hand, it'll take all of your line search points, fit a quadratic to those, and return the vertex of that. Again, just depending on the nature of your objective function, one of these might be more effective than the other. Rsq tolerance is a tolerance for which the R² value, so if you pick a quadratic line search, then Rsq tolerance lets you control how good that quadratic fit needs to be. If it forms a quadratic fit and the R² value is below this Rsq tol, then it will reject that quadratic fit. What exactly it does if it rejects that, I don't remember. I think it might go I think it might default back to the bracket. Because, you know, if you've executed this line search and you look at, if you were to plot the objective function over the distance in that direction, it may not look like a parabola. It could look kind of like an inverted V. It could look like some weird cubic. You don't know what it looks like. And so if it doesn't make a good parabola, then that quadratic line search isn't going to do a good job for you. And so this lets you say, okay, if the quadratic works, then let's keep the quadratic. If the quadratic is not working, then go back to the bracketing method, because that's going to be more reliable. And then Wolf-Armijo and Wolf curvature, these are conditions for restarting the Hessian update. So as Dr. Unsaker talked about, as it's stepping along, as it's doing these iterations, it's the BFGSB, or the BFGS algorithm, is building up this estimate of the Hessian matrix. And eventually over time, you get a lot of history built into that, and that can help you, but it can also hinder you. And so these are parameters for resetting that periodically through the optimization. It kind of gives you a fresh start to it. I don't remember what all these do, but you can read about these on Wikipedia. They give a pretty good explanation. And then there's an option for initializing the Hessian matrix. It initializes the Hessian to this value multiplied by the identity matrix. If you increase this can speed up convergence on some problems, but not always. So it defaults to 1 typically. Anyway, you can play with that, and it may give you a faster performance. So that's BFGS. There are a lot of arguments for BFGS because it's kind of there's a lot going on in that method. SQP is a little more simple. There's only a couple of arguments for this one. One is strict penalty. That's just a Boolean. You can turn it on or off, and that just specifies whether a given step in the optimization must result in a decrease in the penalty function. SQP, like I said, it's not always going to stay within feasible space. In order to handle that, it has what's called a penalty function that penalizes it for going outside feasible space. And eventually you get to the point where the penalty function is 0 and it's satisfied feasible space. But not only is it not always guaranteed to be feasible, it's not always guaranteed that a given step will decrease the penalty function. Now you can turn that on here, and you can make, or this defaults to true, and you can force it to say, hey, at every step you need to be decreasing the penalty function. But in some cases, you can actually get better convergence if you say, you know what, I'm going to trust you, I'm going to let you do your thing. You can have increases or decreases in the penalty function. You can do whatever you want, and it'll get there eventually. For some problems, this can speed things up, and some not. And then again, like the BFGS algorithm, you can set an initialization parameter for that Hessian matrix. And then the final one is the Grg algorithm. Like the BFGS algorithm, it executes a line search, so you can tell it the number of steps you want to use in the number of steps from, or that's the number of steps to use in that line search. Alpha D is the step size to use for the line searches. And unlike BFGS, the way it does the line search is a little different than BFGS, and so how you specify these step sizes is a little different. So if you don't put this in, then it'll just use the step size that was the optimum step size from the previous iteration. And then alpha molt is, again, the factor by which alpha is adjusted during each iteration of the line search. And then constraint tall. GRG is an interesting algorithm because it almost like turns constraints on and off. It evaluates your constraints functions, and if you know you're way far away, it's these fences on your design space, right? And if you're way far away from one of those fences, then GRG looks at that and says, okay, I can ignore that constraint right now. I don't need to worry about it because it's what it's called, it's not binding. But if you're close, if you're really, really close to that constraint, even if you're not touching the constraint, but if you're close to it, then GRG will consider it binding. And so this is a parameter that you can set for, how tight, how close do you have to be to your constraints before they're considered binding. If you're making more constraints more binding, then that slows down the algorithm. So this gives you a little control over that. Anyway, that's all of the documentation for Optix. Dr. Ensaker, were you wanting me to run through run through a demonstration of this, or were you planning to do that?
No, I'm planning to do a demonstration, so I think we can do that now.
Okay, cool.
Okay, great. Thank you, Corey.
Yeah.
All right. So let's look at this. Okay, so what I'd like to do is we're going to do a little exercise here. And so here's our, just a second. Okay, so here's our exercise. What we're going to do is write a function for, we're going to do z equals x minus 5 squared plus 4 times y minus 2 squared. And we're going to start with an initial guess of, let's see, minus 2, oops, like that. And then ask Optix to solve this. Okay, so we're going to work through that. And so I'd like you to work on your own code here. I'm going to show you my code to solve this problem. And I'd like you to basically write your own code as we're going along here. So here's my code. I've got a whole lot of stuff that I'll be going over later. So really, you don't need to look at any of this other than what is not commented out here. So this is what we want to do here. Not this. And also not this. Okay, so the file that so you're going to open a new Python file, and we need to import Optix as OPT or whatever you want to call it. We need to define a function f of x, and actually let's just do that right now. So I'm calling it result. So we're going to say that result equals x 0 minus 5, and that's squared, plus 4 times x1. So remember, x is a vector of input. So then we're going to take component number 1 there, minus 2, and square that. Okay, so that's my objective function. And so it's just going to return result here. And you could just return this right now. You know, you could just put this as a single line in here. There's a reason I'm not doing that. We'll get to that later. But and then you need this call in here. And Corey, maybe you want to explain. This is something with the multi-processing capability of it. So it's just a little bit different how you have to set it up. But had to add this before we, that the rest of this basically is inside of this function here. So Corey, do you want to comment on that?
Yeah, I don't fully understand it. This is really just proper Python coding. When you write a Python script, all of your, I don't know how to describe this. Any functions that you define, you should define up top here. And then all of your script code, the stuff that you just need to run once through this file, you should put inside this if name equals main block. What that does is that kind of separates all your function definitions from your code that you want to run. And what you can do is then you can take this file and you can import it into a different Python script, and you can use all those functions. But since this file is no longer main, that's what it's checking here, if name is equal to main. If that's not true, then it ignores all the code below that. So it makes it really useful for reloading code, but it's required for this multi-processing.
Okay.
So again, I don't fully understand all the reasons for it, but you should get in, if you're writing Python, you should get in the habit of including this if name equals main construct. It's really the proper way to do things.
Okay. All right, so then inside of this, we're going to initialize x. We call it x naught. And let's see, we wanted to start with a value of -2, 2.0, and -2.0. Now, I'm in the habit of adding a decimal but behind every real number. And that's because in Fortran, in a compiled language, there's reasons that you do that. And even in scripted languages, it's helpful to the interpreter to know that this is a real number. Otherwise, I'm actually, if I don't have the 0.0 on that, then this is passed in as an integer. At first, it interprets it as an integer, and then it has to realize that it's being used as a real number and switch it to a real number. But if you, and you can see that I did that up here as well, 5.0, 4.0. Now, squared, when you square that, that is an integer. But you could make that a real number if you wanted to. So when I'm squaring or cubing or whatever, I leave those as integers, but then anything inside the computation here, I just bring it in as a real number, so the interpreter doesn't have to realize that it's a real number. Instead, it's just treating it as a real number from the get-go. So that's just a personal coding practice that I do, and I'm not even sure if it's accepted as the right way to do things anymore, but yeah. Okay, so then we're going to call this opt.minimize. We're going to call this function, we're going to pass in f, that's the handle to this function up here. X naught is our initial guess for x. File tag is test. We'll see what that does here in a second. End search, so that's the number of points in the search in the line search that's going to be run before it makes a decision of whether or not it's hit a minimum in that direction. Max processes, I'm going to set that to 1 to start off. So it's just going to be using a single processor. The line search is using quadratic, termination 1 e to the minus 6. And I have verbose set to true. Okay, so it's going to spit a bunch of stuff to the screen throughout the optimization, and we'll see that as it moves along. Okay, so I'm going to save this. And now let me pull up. All right, let's see. There's a bunch of old stuff in here, but I'm going to run this Optix example1.py. That's what this file is. And I'm just calling Python in front of that. So let's see what happens here. Okay, so it started off and it said, this is optic.py from USU Air Lab. Here's your initial guess. Got 2 variables, information about constraints, which you don't have any. Here's my settings, so it's just printing those to the screen. dx, by the way, so I can see what it's going to use for the gradient for finite differencing. We have verbose set to true. And then basically it's going to print out, this is a column of columns of information, an inner, an outer, and an inner, which I'll touch on here in just a second. And then information for each of these. So at each iteration, it's giving me the fitness, the magnitude of dx, or the I believe that's the stepping direction that it took to get there, and then my x0 and x1 components. And of course, if we had more variables, then there'd be more out here. So these are the 2. So this is x and y basically, right? And then the fitness value, or the objective function. So I can see that this was the initial guess. I initialized it to -2, -2, and then it went into a line search. It computed a gradient. And so here's the search direction. So I can see what direction it thinks it should be going to walk downhill. And then here's a step size that it's using in that line search. And then it's going to run 8 cases in that direction and try to see if the magnitude is increasing or decreasing. And so I can see what x and y are. So these are columns of x and y, and then the associated fitness. So you can see that we are decreasing. We went from 1.1 e to the +2 down to 8 e to the 1, right? So 81 here, and this is 113 up there. So we went down to 81. Well, of course it yeah, so then it says, well, I want to go further. That was too small of a step. I'd like to increase my step size. So now it's increasing the step size to 0.87, where before it was 0.125. So that's just kind of a scaling factor in that direction. And so you can see here, if we rerun that now, we're going from 113 down to 40. Let's see, apparently it's saying that that's good enough. And so it's going to fit a quadratic to that and guess where the minimum is. And the minimum it's saying is at these locations, this X and Y location, and this is the associated value, 26. Oh, just kidding. So we overstepped it here. That's what I was looking for. So we decreased. So we started at 113. We decreased to 85, 62, 45, 33, 27, 26, and then it started to increase again, 31 and 40. So it did capture a minimum inside of there. And so it found out, this is how far I've got to step in order to get to that minimum. And this is the estimated minimum by fitting, I believe it fits a quadratic to the 3 closest points here and pulls the minimum off of that, calls the objective function at that location. And now this is my new point in the design space that I'm sitting. So again, it runs a gradient. It says, okay, here's my next search direction. So it computes differences in each direction here. And then again, it's going to do this line search. It copied over the step size from how big of a step it had to take last time to get there. So that's just its initial guess for it. And again, this one captures a minimum. So we start off at 26, we get down to 5.96 e to the -3. So that's very small. and then back up to 24. And so obviously, and then if it keeps stepping in that direction, then it gets it back up to 124 there. So, so it says, okay, this was my final alpha to capture that minimum there. And this is the location of that minimum. It's at a value of 5 and 2 out to precision, at least. Well, I guess there's a little 2 right there, but otherwise it's out to precision. And so it says, okay, here's a 0, and I believe it's got to call a gradient again at some point to make sure that basically the gradient is really small. And then it says, okay, I've reached the minimum. Okay, so that was the process. We can see all of the decisions that it's making along the way because it's writing them to the screen. And that's one of the benefits of using Optix, is because we wrote it in-house. And so we decided what to print out to the screen here, which is really helpful. Now, if you look online, there are forums about optimization, and some people argue, well, you don't need to know what's happening in the intermediate steps. You just need to know what the final answer is. And I completely disagree with that. I think in optimization, there are so many little gotchas that can happen in a design space. You've got to be able to see what's happening under the hood. And that's one of the benefits of Optix over the SciPy library out there. It's really hard to see what's happening under the hood in SciPy.optimize because they don't have things like this that are being written out consistently. Okay, so let me pull up the output to this. So in that same folder, by the way, so this is the folder that I just ran that in, and here's my code, Optix example 1.py, and it wrote this thing called optimize.test. It wrote this text file. So let's pull up that text file and see what it's telling us. Okay, so what it said is here's our iterations. There's outer and inner, and again, I'm going to get back to what those mean here in a minute. Fitness, mag dx, and x naught, which is our x, and x1, which is our y. So we can see the entire history. It took 3 steps to get to the optimum, 3 iterations, and within those iterations, it had to call the function many more times in order to compute gradients and to do line searches and things like this. So this doesn't say that we only called our objective function 3 times. These were the official steps that it took in the optimization routine. You know, it only took 3 iterations to get to the optimum, okay? It also puts out a gradient file. So you can see what the gradient is at every step along the way. So these were and you can see the final gradient. So it did compute the gradients at that final location. So here's that final location, that's the fitness, and these are the gradients. Those gradients were within the stopping tolerance that we told it to. And so because those gradients were so small, it said it had reached the optimum. And then evaluations test. Okay, so this evaluations, this is every single time it evaluated that function. So here's the function value, and these were the input parameters, x0 and x1. So you can see the very first time it called it, it was calling it right at our at the initial guess, -2, -2, right? That's where we started. And the very first thing it did was compute a gradient. And it does that by first altering the first input, but leaving the second input at what we had it at. And because we're doing central differencing, it has to call it a little bit above and a little bit below in order to compute the central difference at that point. And then it does the same thing to our y value, a little bit above and a little bit below. Now, it didn't have to compute the center point again because it already had the center point here. And of course, actually, you don't even need that for the central differencing. But anyway, so those are our 4 calls right there. It took 4 calls to compute the gradient because we're doing central differencing. Now, if we had been doing forward differencing, it would have only required 2 calls. But of course, we give up some accuracy. Okay. So then after those, then it called a line search. And so the next 8 or so of these, or 16, you know, it took a couple iterations here. These are all line search calls before it got to what it said was going to be our next point, which I think was this 26, eventually was the minimum. And then again, at that 26, it's going to do some perturbations. So it's going to, in order to compute the gradients, so you'll see small changes here for the gradient, and then more calls for the line search. And then finally, these were the final calls for the gradient down here. So eventually we got to this point, and then we had 4 more calls to compute the gradient. And so again, you can see little perturbations in the first value and the second value to compute those gradients. So this is a history of every single call that was made to that objective function, which is, again, very helpful for debugging things, for understanding what's going on. Okay, so those are some things that Optix outputs, and now we can up the number of processors. And like Corey was pointing out, one of the big benefits of Optix is that it is parallelizable. In fact, let me come back to this for just a moment. So each of these calls, we can look at which ones are independent of the other calls, in the sense that it didn't matter what the solution was to the previous call before it knew what it needed to call next. So for example, the very first call that we have is at the location. No matter what that comes back as, we have to compute a gradient. So actually all of these calls, the location and those 4 calls for the gradient, could all be made simultaneously. We already know from the initial guess what the first 4 calls are going to be. But we have to know the results of this, because then we're going to compute a gradient to figure out what the search direction is going to be. And then once we know what direction we're going to search in, then we can call 8 or so. Now, I think I had it set at 8. So that's one of the inputs here is end search. How many points in the search direction do you want to call before you evaluate whether or not we've captured a minimum? And so we had that set to 8. So it's going to call 8 of these, and it's going to wait until all of them return before it makes a decision about how far to step to capture the minimum. So all of those can be called simultaneously if we're multi-processing, right? And then it's going to evaluate those 8 and say and decide whether or not it captured a minimum. If not, it's going to call another 8. And so, the next 8 calls are also completely independent of each other. Eventually, it's going to capture a minimum, which we did down here. And then the next derivatives off of that, again, we have 4 more calls to get the derivative. And so all of those calls can be made simultaneously. So these are things that can be easily parallelized. Now,
can I ask a question really quick, just for clarification?
Yeah.
The first 4 calls are using central difference method, correct?
Mm-hmm.
To get the gradient. The next 8 are randomly selected points to find out where the minimum location is.
They're not random. They're
random.
Yeah. So basically what's happening is it's running a line search. If we come back over here, I think I had a drawing of this at some point. Here we go. So once we find out, we're sitting here in the design space, for example, I'm sorry, we start right here. Here's 1. So we have our initial guess, and it computes a gradient. So it computes 4 calls to figure out what the gradient is at this location. And that gives it a search direction that it needs to walk in. Now, you could just first you've got to choose a distance to step, right? How far, so we have a gradient. How far are we going to step here? Well, because we only know the first derivative, we don't know the second derivative, we actually don't have a good guess for how far to step. We really don't know. Mm-hmm. And so so that's one of the settings in here is, what do you want to use for your, well, it's a setting that you can change. There's a, I think the default is 0.125 in the documentation, but you can change that. But anyway, it's just going to basically take that number, I think, and multiply it, by the search direction to compute a search step size. So, it's anybody's guess how far we're going to step in this direction. We just really don't know. And so we just have to choose something and go for it. So, if you wanted, you could just, choose a step size and say, did that go up or down? If it went down, let's keep going. You could double the step size. You could double it again. You could keep moving out here until it moves down. But I guess the benefit of saying, no, I'm going to run 8 of these before I make a decision. The real benefit is if you can parallel process, you can run 8 at the same time. You can run 8 calls in the same time it takes to run one call if you have 8 threads on your computer or 8 processors on your computer. Does that make sense?
I was wondering how, because you have to compute the gradient, and then you're calculating these 8 points simultaneously instead of one, then the next, then the next, then the next.
Exactly.
Okay, that makes more sense.
I guess what I'm saying is Optix is set up to do that as long as you set the number of processes here as the same number as the search. Does that make sense? Then it will call all of these, and so I'll just change that right now. It will call all of those simultaneously.
Okay.
If, you know, and it will let your processor try to compute all of those at the same time. And so back to what Corey was saying before, if your objective function takes a while to run, which is the case for many of the things that we do in our lab, you know, it might take a few seconds or a few minutes to run. And we have the ability to run those on different processors simultaneously, then it's a lot faster. You know, in this example that we're doing here, you're not going to see any difference in the compute time because the time it takes to call this function is so minuscule, right? But
Dr. Unsaker,
yeah,
if you did want to demonstrate that, you could add a sleep function inside of your objective function.
okay,
And we could see the difference real quick.
okay, let's do that.
So-
So
Right at the very, very top, you'll need to do import time.
okay,
And then the syntax is time.sleep and then parentheses number of seconds.
okay. So what if I do 2 seconds?
Yeah.
Okay, so let's go back to 1 here. So we'll just see. So I'll just rerun this. Okay, so it's going to take 8 seconds now to compute that gradient, right? 2 seconds per call. Okay, so there it's got a gradient. And now it should be just, well, it's going to call 8 of these, I think, before it even displays this. We'll see. Maybe I should have set it to 1 second. Okay, there you go. So it took 16 seconds, right, for it to compute all 8 of these because it's just doing them one at a time. And again, if we're going to do it only one at a time, then we might as well be evaluating, you know, between every call, whether or not we've hit a minimum. Does that make sense? But if we can multi-process, then we can call all 8 of those at the same time. And so you usually want to set the number of search terms here equal to the number of processors that you have, you know, the number of solutions you can be running simultaneously. And that's completely machine dependent. So if we're running this on one of our bigger machines in the lab, then we could be calling 32 at the same time instead of just 8.
Thank you, guys. That clears a lot of the parallel processing.
Okay.
Like that's been confusing, so that was helpful.
Okay, let me rerun this now and say we're going to use 8 processors. Now I'm not sure how my computer's gonna. We'll see how this goes. Okay, you see, it got the search direction very quickly. Oh, yeah, and each of these are taking about 2 seconds because it's running all 8 at the same time. And it can compute all of those derivatives at the same time as well, you know. So you can see the time, the speed up in time there. I guess I could have clocked the time here as well, but. Okay, good question. Thanks, Kyler. Okay, let's see. I think I've pointed out everything that I wanted to on that case. What I would like to do next is to have each of you choose a function. Actually, let's do one more thing before we do that. Let's switch over to scipy.optimize, okay? And run this exact same case. So what I'm going to do is I'm going to block out Optix up here, and I'm going to instead import scipy.optimize as SO. And the setup for this is a little bit different. I'm going to turn off the sleep function. And the setup for scipy.optimize is a little bit different. And I've got it right down here. So we've got X naught. We're going to initialize that to -2.0. minus 2.0. And we're going to say optimum equals so.minimize. And again, I'm going to pass in the handle to that function, my x naught, which is the initial guess. And then I'm just going to set the method to BFGS and use the defaults. And then I'm going to print out whatever is returned in optimum. And so just like in this Optix, what comes back from this is a whole bunch of information about how things ran. And so you can get the optimum value, the optimum point, the number of function calls, which, by the way, I think there's a typo in here, Corey. That number right now calls 2. That's really the iteration. It's not the number of function calls. So
okay, I'll have to look at that.
Heads up there. So anyway, I'm just going to print out everything that it will give me in this optimum variable when it comes out of this. Okay, so I'm going to rerun. This is the exact same problem, and now I'm running it in SciPy instead. Okay, so so first of all, you might see an enormous performance increase, right? So it already found the optimum. It's all done. It's saying that it's at 4.9997 and 2. And of course, this error here is because the default is to use forward differencing, not central differencing. And so I believe I can force that. I'm not sure. Is that one of the settings here in, I'm actually not sure we can change that in SciPy to optimize. Does anybody know? We can do central differencing.
I believe, let me see. I thought there was a setting for it. So let me check that.
Says it uses finite differences, but I'm not seeing how it does that. Anyway, I'm fairly certain though that error in that final solution is due to forward differencing instead of central. It could also be that there's a default exit criteria for how accurately we want to know this information. And so you can see the Jacobian, which is basically our derivative, is down to e to the minus 8, where before the derivative, I'm not showing it here, but was down to e to the minus 12. So the derivative from Optix got a lot lower, but we also had set the convergence criteria on that slightly different than we have here. Okay, so the final value for the function is 0 out to machine precision. The number of function evaluations was 27. Number of iterations, it took 8 iterations. Ours took 3 iterations. And I'm not sure how many function evaluations. I think ours takes more on the order of probably 30 or 40. But anyway, so a few less function evaluations, a few more iterations. The number of Jacobian evaluations was 9. And it was successful. And here's our final value. Okay, now this was a lot faster. You probably noticed that. This was extremely fast. And part of the reason for that is that under the hood, much of this is compiled. And so, you know, we think of Python as a scripted language, but under the hood, there are many components of it that are compiled. And because this was so fast to compute, it can basically like inline that and compute it very quickly. Let's add this sleep now. So let's give an extra 2 seconds there for each evaluation. And we'll feel, you know, it's going to take 27 times 2 seconds basically to solve this, which is going to be, you know, what is that, 54 seconds, so about a minute to solve this. And so that's going to bring it on the same order as this other one when we were using multi-processing. I guess I just want to point out that this is so fast because it's probably got compiled components underneath the hood, and because our objective function just hardly costs anything to compute. Now, one thing to note is that there's really no way to get more information out of this than what we have printed on the screen right now. You can't set more flags. Like maybe there's a verbose flag or something where you can get a little bit more information, but you can't get nearly the amount of information that we can out of Optix. We can see every decision that is being made by Optix. And so the way to fix that is to actually put a print statement inside of your function here. So every time this function gets called, I'm going to print out X, Y, and the result. Okay, that's really about the only way I have of forcing SciPy to optimize to tell me or to show me what's actually happening. Okay, so now I'm going to recall that, and I'm going to cut this down to 1 second. So that'll take about 30 seconds to run here. And so now we can see every single call that's being made to that function. Okay, so you can see one of the first things it did here was compute a gradient, right, by perturbing the first number and then perturbing the second. So it's certainly using forward or backwards differencing. And then it's got to be performing some line searches. So one last thing I'd like to do before I let you guys loose on another project. And actually, Ammon just said, he said to use central differencing with SciPy, pass it the argument Jacobian equals 3 points. Let's try that real quick. So we just say, I guess I'll put it down here. Okay, let's see if that works. It's going to do, yeah, it did. So you could see those first two calls there. That was the Jacobian, so it's doing a little bit above, a little bit below. Thank you, Ammon. Okay, so while that's running, I'm going to just grab this and copy it and drop it in a text file. And I missed the very first line of it here. Okay, now what I want to do is I just want to see where it's how it's walking around in this design space. So I'm going to drop in. So this is X, Y, and F for the SciPy to optimize, and this is same thing. Some of these got shifted. I'm just going to fix that real quick. Okay, so this is a time history of calls, basically. Now, let's actually keep this apples to apples. Since this was using central differencing, we're going to actually do that instead. Okay, so these are the calls. This left one is from SciPy.optimize. So this is SciPy, and this one is Optix. Okay, and I guess just to keep these all the same, I'm going to rearrange this so that it's all the same here. Okay, so what I want to do now is plot. I just want to see how it's walking around this design space, and so I'm going to put in something like that. So that shows me where we started and where we ended. We started at -2, -2, and we ended here at 5, 2, right? And I'm going to do the same thing for this other one. So this is X and Y. And okay, now I'm just going to overlay these. Of course, they both start and end at the same locations. Okay, so Okay, so you can see the orange one is SciPy to optimize and it took, what was this? So 1, 2, 3, 4 iterations to get there. We take 3 iterations, but I'm actually, I'm plotting every single call that was made in Optix. Okay, so you can see we started right here. This is our line search. We could tell that this was the direction we had to start off walking. And you can see that's the same direction that that SciPy also walked in, right? So it basically, but Optix, or excuse me, SciPy to optimize stopped right there. I'm not really sure why, because if you keep walking in that direction, the real minimum is over here, right? So somehow, and we're using the same method, you know, these are both BFGS methods. So again, it's really hard for me to trust sometimes what's happening in SciPy to optimize. And probably a lot of it is that I'm not an optimization guru or expert, but I don't understand how it makes some of the decisions that it makes. But in any case, it decided to stop right there. You can see that's where the orange one stops as its next step. And then it takes, and then it computes the gradient again, I'm assuming. We could go back and see that in the time history, and then it walks in this direction, computes the gradient, walks in this direction, computes the gradient, and walks down here. Somehow it's making those decisions, but the decisions that Optix is making is it starts here, it runs a line search to here, it realizes that it hasn't reached the minimum yet, and so it doubles that line search, and it comes clear out to here. So again, these are the 8 points that it's running simultaneously if we want it to. So it ran points clear out to here, and from that it bounded it and said the minimum is right here. So it took that as its next step. Then it computed the gradient, and the gradient pointed in this direction. So it ran 8 points in this direction. So that's why we have all these points out along here. And it says, well, the minimum is right there, and bam, we were there. So it was 3 steps, 1, 2, 3, it found the minimum. SciPy to optimize took 4 steps to get there. And I do not understand. Now, both of these, by the way, let's just point out, both of these are using central differencing. And so you can see that this left one took, what are we at? 45 calls. And the right one, Optix, took 39. So Optix was able to solve it in less calls to the function than SciPy was able to. And they took different paths, even though they're using the same algorithm. Okay, hopefully that's insightful. You know, these are the things that are really helpful for debugging and learning what's going on underneath the hood. So what I'd like to do is have you guys each choose a function now. And basically, if you have this code written up now, it's very simple to switch out the function. So this is the example that we just did. I've coded in a bunch of different examples here. So this is Himmelblaus, the 3-hump camel, Rosenbrock, Matthias, the sphere function. And so what I'd like you to do is grab one of these test functions. And again, I'll drop this link in there in the chat for you. And we're only going to be looking at 2-dimensional optimization here. So X and Y. So here's like a Booth function, you know, it's a function of X and Y. Now, some of these are n-dimensional. So for example, the Rosenbrock, you can have as many dimensions as you want. I'm only, when I coded mine up, I'm only including X and Y, right? So the first 2 components in this series. There's a sphere function, Ackley function. Anyway, you can choose any of these, but if you're going to choose one that has an infinite number of inputs, basically, we just want to include the first 2 inputs, all right? So I'd like you to just choose one of these functions, something that looks kind of interesting, and we're just going to run some optimization cases on these using these different algorithms and see how they behave, all right?